Oh, hello there. Well, guys, what's going on? Memes here. Yes, yes, we're going to be going through, and again, conjecturing that perhaps, given our system of units, um, there may be the slight chance that we got things incredibly correct. And again, this is speculation. Again, full disclosure, I don't have a PhD in mathematics, and I'm not a quantum mechanic. A crazy person on the internet that, well, perhaps like a lot of y'all, is extremely interested, has had the benefit of 100 years since our standard formulation of quantum theory, at least as we know it. It's been 100 years, at least according to Professor Barondus and Wolfram there, that perhaps utilizing the past 100 years of knowledge, hard fought and I would claim successful experiments, we've been able to probe into reality to try to figure out what might be going on. It also doesn't hurt that we have modern computational tools like Wolfram Alpha and everything, so like a stumbling idiot like me can just be like, here's a word, here's a thing. Oh, here's all these different relationships that I didn't know. It's kind of within Professor Wolfram's whole idea of, let's say, computational X. That might not be the most satisfying thing just saying that there, but the general thought is, well, if we have things and we have the ability to symbolically manipulate and everything, and I'm just starting to learn how big a deal certain things like Mathematica actually are, so people didn't have to always write their own code. Um, Long story short, I'm basically just a monkey with a magic typewriter and maybe a few hints on potentially where to look. I'm also probably a little bit spectrumy and kind of a gamer that's like, ooh, let me do all these combinations. Let's see what happens, just for even my own thought process. And again, most things are trivial. They probably don't mean a dang thing. It's just like, oh, I'm just an idiot. I just didn't know this. Going to hours and hours down. Oh, okay. I'm not gonna bore you with all my dead ends and everything because we're here to potentially say take a look at some relationships that are interesting. Uh, Welcome, Rick. Wait, well, to be fair, a lot of early computers were technically quote unquote women because they were the folks actually doing the calculations. I had interesting conversation the other day. Rick, you were there for the first part of it, where eventually got to the point where they're talking about like some of the early NASA astronauts and everything, and some of them had some questions, and they're like, there was some administrator, somebody said, no, 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 we want to talk to the ladies. Why? Because the ladies actually did the calculations and everything. So if you want to get the oh god, I don't want to say straight from the horse's mouth. That's terrible. But if you basically you want the rawest information that you can, and then you're going to go through all these different processes and everything. But yes, welcome violence. That's the internet's a fun place because that's one of the few places I can be like, welcome violence. All right, so let's get into it. Hidden Figures, the movie that I Hidden Figures movie 2016. Why does this almost look familiar? Is this about? Oh, this literally is a movie. It's got a. It's about according to Netflix, three brilliant black women over. Oh, geez, that's yeah, back in the day. Yeah, yeah, yeah. It's yeah. This some things of history you don't hear as much about, but history was a thing. We've been there, and I think we should probably move forward. It's my opinion there. All right, so let's get straight into what the heck I'm talking about here. All right, so I showed a bunch of things. Maybe we'll just go through actual thing. That's Professor Barondus. Let's go over here. All right, so what the heck am I showing here? Let's oh, where is that? There we go. All right, share with the class. What are we talking about today? What we're talking about today is the interesting coinky dink. Let's say that because let's take a look at the Newtonian gravitational constant on the Higgs parameter linked potentially to the Joule second. Okay, and there's a whole bunch of stuff there, and you're seeing this thing. What the heck is this thing here? I said big G, there ain't no big G there. Okay. We're getting there. We're getting there. Basically, this was the most computationally reduced version of what I could get this to. So this whole 3.4 times 10 to the minus 26 newtons Newton is the SI, or just the metric system unit of force. Okay. Yeah, high school, F equals MA, and then you can get most of physics, apparently. All right. So the whole point of this thing right here, this is the constant of proportionality, essentially the force, if we were to input the Higgs boson with, again, some conjectured parameters, we get interesting results. And again, we're going to have to follow experiment. Could be totally wrong, but this number that we have in here comes from this thingy here. So this is big G, the Newtonian gravitational constant. So we need mass 1 and mass 2. For that, literally just taking out the calculated, and again, conjectured mass of the Higgs boson. That like 10 to the minus 25 kilograms. So we got it squared. So mass 1 times mass 2. So if you're putting in the same thing, you can just square it. Okay. And then divided by r squared. This is basically just the number you get out for the Compton wavelength of the Higgs boson, based upon this calculation. We'll go into that in a second. Again, it's, oh no, numbers and stuff. It's literally, a lot of it is just words. But again, Wolfram Alpha, it is going to round, and it does have generally pretty good information, but you're going to want to go to the actual experiments and everything and actually see what the measured values are. And if you're going to be outside the 1 sigma so range, now you're going to have a reason for that, a good explanation. Now, maybe your explanation is wrong. Maybe it don't hold water. But I'm of the opinion that there is a way to figure out what might be going on, and it should hold water. So, long story short is you put all this stuff in there, you get this number here. Okay. And this number here, I noticed, just because I'm a crazy person, that seemed to be about the magnitude of Hbar times C, which is essentially interpreted as bending stiffness. So let's just get into it before I randomly just keep showing this dang thing. So, oh, that's what it was. Okay, John Glenn was waiting for the ladies to confirm the actual go, no-go numbers. Well, if your life is on the line, you're going to want the calculations to be accurate. Yes, we're going to go into big G right now. So let's share these tabs. And again, it's just, might just simply be a coincidence. Maybe we actually did something incredibly right. I mean, what are the chances of that happening? That would, I think, by definition, be a miracle. Okay. So first things first, this is the conjectured way, or the mass of the Higgs boson. So what were you doing? So what we're doing is, this is the Planck mass from CODATA. Just straight from there. It's got error bars of, I think, like 2.4 on the last 2 digits. So that could go up to 5.8 or go down to 1.0. Okay. But this is just the straight. This is what we believe based upon our calculations, the recommendation from CODATA. So it gives us a couple extra digits, but we must note there is error in those digits. So keep that in mind. Okay, so what we're doing is we're taking the elementary unit of action. We are dividing it by the reference of action. So Hbar, Planck's reduced constant, is in units of Joule seconds. So basically it's a mass area rate. So you got a mass, you got some area, perhaps some surface or something. It's divided by a unit of time. Okay, and that's what we call action, aka it's energy seconds. Because when we multiply energy by seconds, mass, c squared is just length squared divided by time squared. When you put another second in there, it's going to cancel on the denominator. So hold on, it's just easier to show this. So I just do energy. Okay, so you get the Planck mass, you got your c squared there. So what is it? Mass, length squared, divided by time squared. Multiplied by a second. And then all of a sudden, we get Joule seconds, which is angular momentum, action. Because what happens is we multiply by a second. So you get 1 unit of seconds of time. In the numerator, it cancels out 1 in the denominator. So that's all that is. That's speed. I mean, this is the only reason, just because it's simple. Again, it took me a couple of years to actually be able to start a grok, so to speak, what might be going on. But that's the claim. And again, maybe it's just totally bunk. It's a very beautiful thing. It might help explain a lot if there was some there, but we're working on that. It needs to be more rigorously formulated to see what might be happening. Okay. Just a second. All right. So what we got here? Okay. So what we're doing is we're taking the elementary unit of action, we're dividing it by its reference unit of action. Okay. It's going to give you that 10 to the minus 34 that basically Hbar is. But it's dividing the dimensions out. We take the square root of that. Okay. Gives you like a 10 to the minus 17 number, which coincidentally happens to be about the magnitude difference between the Planck mass and the Higgs boson mass. And then you multiply this by the Planck mass. Basically, you get the Higgs boson mass. And again, Wolfram alpha typically uses about 3 significant digits there. So just keep that in mind. We're doing this out to try to eke out perhaps a few more significant digits based upon this claim or conjecture, if you would. And we're going to see what we get. Okay. So we get all those numbers there, and it gives us, this is our 10 to the minus 25 kilograms. Okay. So if we go ahead, and, oh, I should probably actually, where was that? I need to go into the Compton wavelength. Oh, did I not actually put that together? Okay, so let's just do that here. So since we have this mass, there's a little trick. And there's something that Professor Carroll had also mentioned in his recent AMA couple weeks ago, I think, is that there is a way you can convert from a mass to the associated Compton wavelength of a particular particle or whatever the heck we believe particles to be. I think they're a useful idea. But basically you take Planck's constant, not the reduced, the one with the 2 pi factor in it. So you take Planck's constant, divided by the mass, times the speed of light, and you're going to get a wavelength. Okay. So when we do this, we get this really small thing, that 9.8. So it's about 10 to the minus 17, which is basically the range of the weak nuclear force. Nuclear force. I apologize. I apologize for my Bushism. All right. And then you look at this, you're like, oh my god, it's about 100. Okay, I'm just checking real quick because I don't think it is, because it doesn't say 137, but just in case, because Wolfram Alpha does okay. It gives us a different number. Well, that might be a discussion for another day. We'll get there at some point. Okay. So we've got an associated wavelength now. Okay. Cool. So since we've got a conjectured mass and a conjectured wavelength, let's plug them into just our normal big G expression here. Okay. So what we got? We got the Newtonian gravitational constant, big G. We've got our mass 1 and mass 2. So we're just taking the same mass, our claimed mass of the Higgs boson. We're squaring it, so we get 2 masses. And then we've got our R squared, so we're just putting in the associated Compton wavelength at that particular mass, and we're squaring it. It gives us this number here, 3 0.409 times 10 to the minus 26 newtons. Don't worry. I have no idea what that is. It's just some number in the dimensions of force. A mass length divided by time squared. So mass times acceleration. Okay. Now, I just look at this number. I'm like, that seems to be of the magnitude of something I know. What is it the magnitude of that I might know? Don't mind me. It's about the magnitude of Hbar c, which is also at the minus 26 magnitude. Okay. What's interesting about this, because number one, it's interpretation, and there is more than one interpretation, is bending stiffness. Because you're talking about the elementary unit of action times the maximum of speed. Long story short is, it's got a mass, it's got a volume, because it's length cubed, divided by time squared. Long story short is, it's basically big G except with mass in the numerator. Because if you put these in Planck units, you put mass in the denominator, well, big G, you're doing a unit. You got mass in the denominator. You got a volume divided by time squared. And back over here, we've got mass, a volume, divided by time squared. So literally, we just moved the Planck mass into the numerator. Gee golly. Is there something interesting that's going on here? Long story short is, and again, I never would have seen any of this stuff if it wasn't for Wolfram Alpha, because you look at it and it gives you unit conversions. So you get 197.3 electron volt nanometers. It's like, I don't know what that is, but this is 1 Hbar c, because, well, that's what it is. Product. Okay. And then if you had Planck's normal constant, yeah, that's just 1 over 2 pi. Okay. But you got this crazy thing here. 548.14 image potential energy constants. What the heck is that? May or may not be Hbar c divided by 4. Fine. Oh, sorry. I wrote it twice. Structure constants. I might have that, might need to divide it into the fine structure constant. Yep, I did that wrong. Okay. It's Hbar c, and then instead of 1 over 137, it's a factor of 4. Why is it a factor of 4? I have no idea. This has something to do why, in order to go from the classical proton radius to the Compton wavelength to its actually measured radius, it's a factor of 4. Does this have something to do with it? I don't know. Because when you put all that together, you get... sorry. More. You get 1B image potential constant. What is that? Oh, it's just this thing here. It's obviously 5.776 times 10 to the minus 29 newtons per Newton meter squared. Coincidentally, it also seems to give you the tail end of the fine structure constant, except it's off by a factor of 10 in these units, and it doesn't have 137 over it. Just because, let's just do this. So it should be, let's just do this. Fine structure constant. It's 1 over that. Okay. So notice, 35999. Okay. We got a 0, 3, 5, and we got at least 3 9s, and then we argue about the 10th decimal place. Okay. 35999. We got the 0 there. Where'd our 137 go? I don't know. But that's just like a little fun, little extra thingy there. So, Rick is pointing out, yes, h bar c is Planck energy times Planck length. Yeah, no, that adds up because energy is mass, length squared divided by time squared, you times another Planck length up there, and then you will get bending stiffness. Oh, yeah, it actually, I didn't even really realize that until I was working on the project. It's like, oh, wait, if you do this here, you get this. If you do this here, you get this. It's like, it's funny how just something like energy or whatnot, a little change in time or length can start to tell a very interesting story, I claim. Okay. So I realize I'm sputtering on. So long story short is, let's go back. All right, so when we do our, don't mind me, when we do our big G thingy there, we've got that. That's about the same magnitude as h bar c. Oh, and just to cover our other bases, you can do the same thing with Coulomb's constant, and unsurprisingly, it does the same thing. But basically, you need to express your mass in terms of energy. So if you express it in the energy here, you basically, let's do this. Okay. So we got that energy. We want to convert it over to something. So basically, if we want to turn it into charge, how the heck do we get charge out of this? It's like, well, if you want to get charge, well, how would we normally do it? We would do, got energy, so we do Planck energy divided by Planck voltage. You can just look this up. This is just the relationship. Basically, it's going to give you the Planck electric charge. Because energy divided by voltage gives you charge. It's just what it comes out to, electric charge, which is time times current. Time times current. Time times current. Wow. Well, maybe that's... we go back. So, long story short is, this is the one of voltage. So as Professor Carroll did also say in one of his recent AMAs, it was one of, like, on field theory, I think from like 2 or 3 weeks ago. He was saying that, well, if you want to have an actual relationship between something, you would divide it by something that would be kind of a natural unit, so to speak. So if you were to divide like the electron mass into the Planck mass, the proton into that, or something like that, that's going to give you a ratio. Because it's like, well, within our system, we have these ratios between two things. Again, I want to use the term gauge. For mathematical reasons, I don't like to use that, because I'm sure there's more involved. But basically, it does seem to be, at least if you're getting a dimensionless ratio, there ain't no dimensions on that, so it's, take it as you would. So long story short is, if we take, let's just do this. Let's do one at a time. So if we take, I should have probably broken this out better, but oh my God, stop opening other things. All right, there we go. All right. So we take an energy, we're going to divide it by a voltage. We're doing the elementary voltage, or perhaps I believe this is a maximum of voltage. A limit, let's say, gives you this. Okay. 0.19 femtocoulombs. What the heck is that? Long story, it's basically 1.96 coulombs. Times 10 to the minus 35, because an amp per second is a coulomb. Okay. The long story short is, we take this whole thing, and we just do exactly what we did. So we do our big G. So this gives us a unit of charge. So charge 1, charge 2. We just square the thing, so we got 2 units of charge. We do our same r squared there, and we just multiply by Coulomb's constant, the same as we did for big G. And unsurprisingly, it gives us that same 3.409 times 10 to the minus 26 newtons. Fantastic. We get the same proportionality. I mean, this really shouldn't be a surprise because it's, well, you got an equation and they both kind of link at Planck units. If you throw in the Planck charge for this, actually, let's just swap out our normal units. Okay, so all we do is, if we wanted to swap this out, all we do is swap it from this unit to the conjectured mass of the Higgs boson. So we go from the Higgs mass to the Planck mass. We square that. And instead of the Compton wavelength of the Higgs, we just do Planck length. Throw our big G in there. It's a unit. And coincidentally, oh look, we get Planck force. Okay, so we throw in Planck units. So that's kind of the whole point. Okay. And then if you were to change this, let's go back to what we had. Go back to the Coulomb version. So rather than all this jazz to get a charge, we just literally throw in the Planck charge. Go back to our Planck length. All right, and then we get the Planck force again. Okay, this is nothing new. I mean, people know this, and this is probably also one of the reasons why a lot of folks are like, these equations seem to be the same thing. It's like, you got a constant of proportionality. You've got some thing. You got either a mass or a charge squared, and then divided by your inverse, and then your inverse square law. So you divide by your r squared. Sometimes give you a Planck unit of force. We go back. It gives us this unit of force. And again, this number doesn't mean a dang thing to me. It's just some really small thing, so we're not done. But as I've bloviated for the past 15 minutes, going on tangents to help catch some folks up on interesting things, let's actually go to what might be going on. Okay, so that's about the magnitude of Hbar c. That happens to do with bending stiffness. So basically it's big G again with mass in the numerator. So what can we do with this? We don't need that. All right. So we take this unit of force and let's just divide it by Hbar c to get perhaps a more manageable number and see what's going on. Because, well, this is the bending stiffness of reality. That might be important. Hbar c and big G are also the things that you'll see in basically all the Planck units. Not the Planck charge. You do not see big G in the Planck charge, which is an interesting thing. And again, when we're going through radical powers, Rick did highlight that. Might there be something interesting going on there? So we divide that in there, so we get a much more manageable number. So we get 1.078 inverse meters squared. So reciprocal meters. You look at that number, I tried to parse it, I'm like, I don't know what that means. So again, I try a whole bunch of crazy things, trying to see, is there a closed form? What can I perhaps figure out? Long story short is, what I figured out was, this was too complicated for me, so I'm like, it's reciprocal meters squared. So it's meters to the negative 2. So I'm like, what if I simplify? Let's just take the square root of this. Because we can do that, because it's a unit. It's got a 2. So we can take the square root, and we get this. Okay, it didn't change much. 1.038 reciprocal meters. Still doesn't mean a dang thing to me. So was it down here that maybe I got a clue? Maybe not. Okay. Long story short is I just kept playing around. I kept playing around, and basically this is where we got. Okay. So I found is, well, that was reciprocal meters. What did I need to have it do something interesting? We took that whole number output there, that 1.38 reciprocal meters. We just divided it into the Planck momentum. So what that ended up doing is, since we got inverse meters in the denominator, that's going to flip it from an inverse meter, since we're dividing it, so it's going to add a unit of meters to the Planck momentum. And the Planck momentum is just your Planck mass times the speed of light. It's a mass, distance, rate. It's momentum. You got a baseball. It's got so much momentum. Okay. But since if you add a unit of meters in the numerator, you actually get Joule seconds, the unit of action. That mass area rate, because we went from just momentum, which is, again, this thingy, a mass times the length divided by a time. You get a momentum. Beautiful. Okay. What happens if you multiply it by, or divide it by, meter to the -1? Okay. It's going to give you meters squared, aka it's going to give you Joule seconds. Okay. There we go. Now, what is the point of this? Memes, why are you even having this here? Why have you been rambling on for half an hour? Because when you do this, you get another number. You get 6.283 Joule seconds. Now again, that by itself probably doesn't necessarily mean anything to much anyone. If you lop off the units, what is 6.283? Is there a potential closed form that maybe we could parse? Oh. Seems to be the beginning of 2 pi. Well, that's a useful thing. We go back. So, basically, long story short, this whole jazz leads to, you take the constant of proportionality between the Higgs. You just literally do big G, Higgs mass 1 times Higgs mass 2, all divided by Higgs Compton wavelength times Higgs Compton wavelength. So, mass 1, mass 2, divided by r squared. Just put in parameters from the Higgs from this calculation. Okay. We divide it by bending stiffness of space, reality, our Hbar, our C, the important building blocks of reality as we know it. We take the root of that. We multiply it by 2 pi. We divide it in the Planck momentum. We get 1 Joule second, aka 10 to the 7 erg seconds. Again, I personally think the erg and other erg-related units, like the erg second, are very underappreciated, often depreciated units. But, I don't know. Anytime you can kind of find a factor of 1, that is interesting, I guess. Yes, welcome, Poindexter. It's, here's the thing. This really shouldn't be surprising to me because that was my original kludge to kind of get here. Because, what did we do? We literally just did, hold on, what is it? Just looked at the Higgs mass divided by the Planck mass. I'm just throwing the brackets because it makes it look prettier. I square this thing. I'm like, just because I'm a crazy person, I'm like, it's 1.05 times 10 to the minus 34. that appears to be at least the first couple of digits, and correct magnitude power without the dimensions, full disclosure, yeah, of Hbar, the elementary unit of action. So I'm like, what would I need that to be to have it be Hbar, or at least according to the information that we have input here? Well, you have to multiply it by the Joule second. Multiply by the Joule second? Oh. Well, it seems to have about 3 significant digits accuracy with the reduced Planck's constant Hbar itself. And now you can, here's the thing. You don't necessarily want to do this equals Hbar. Now maybe it's a little bit off here, so okay. So within the error, and again, this is just a rounding thing. I submit a ticket here. But at least on Wolfram Alpha, again, it has limited data, so take this with a big grain of salt. Your Higgs boson mass divided by the Planck mass, you square it, you multiply by the unit that we have defined, because a Joule second is literally kilograms times meter squared divided by seconds squared. It's... I mean, this is, again, I'm probably missing something incredibly important, but meters squared divide by seconds squared. Meters over seconds, I mean, these are just the dimensions of energy. Okay, so that gives you 1 Newton meter or 1 joule, gives you 10 to the 7 ergs. As we can see, it's a depreciated unit, which is unfortunate. It gives you all these things. Okay. We get the mass of 1 joule, relativistic mass. Okay. So we've literally got there kilograms, meter squared, seconds. Okay. Why does this at least seem to approach the mass of... I mean, why does this seem to work? And again, it's like, it is kind of off there, so you could always just put in there, because we only know the Higgs mass to about 3 significant digits. So let's set it equal to that. Solve for x kg. And we get a number in there, since what it's literally doing is it's just taking the Planck mass, it's squaring it, because, well, this is, when we were going through that dimensionless thing the other day, this is the number that pops up. So that's literally just the Planck mass squared, but we're also solving it in there. Or technically, I think that's the inverse Planck squared, mass squared. Okay. See our things there. And I give you these terms. Again, note, if we're solving it in this form, it does give a positive and a negative value. Is that negative value useful? Depending on who you ask, perhaps that is a missing piece, but I don't know where to put that at all, so I usually just do the square root of that, and we avoid having to do that, and something about a non-negative mass conjecture. Again, I don't know, this seems to be an interesting potential relationship, and again, we're going to have to go by what experiment and logic tells us. I can just hand wave and say, oh, blah, 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 this solves all these things. I mean, maybe. I don't know. You need to have a preferably rigorous, at least up to the standard of a physicist, and preferably more rigorous, way to explain what the heck is going on. Okay. So we get those numbers there. All right. So basically, this was the kludge that I need to put in, and the first thing that I get told is, well, that would mean the Joule second is meaningful. Yes. And part of this is, okay, I'm inserting this. This is a human-created unit. How the heck can I justify this? Well, I don't know if this is proper justification, but I don't know. This is the Planck unit. This is big G, along with, again, conjectured versions of what... Oh, actually, let's do this, because... I think I've got the whole thing in Planck units somewhere. Where was it? This guy, this guy. Where did I put you? Apologies. Oh, is it another thing? Hold on, let me reopen it. Oh, worst host ever. God, professional YouTuber. Was it this guy? I am so bad. Where do we... Oh, God. I'm literally the worst. I still have the tab open, don't I? Hold on. We're conjecturing. Let's play the Wolfram thing, so... Give me, like, 31 seconds. I'll be right back while I bring that up. Where are you? Here we go. All right. You've been warned. We're going to hack the universe, or at least attempt.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Okay, so this abomination right here is basically the whole thing. So let me just throw this in the denominator. So clean it up a little bit. 2 pi. There we go. Okay. So long story short is, let's break it down. So literally, again, just putting in the units we have in Wolfram Alpha. If you don't want to have to do all those numbers and everything, just for a first level approximation, we've got our Higgs particle just from the Wolfram database here. We're taking its mass squared. So we got mass 1 times mass 2. We've got the Compton wavelength associated with the Higgs boson. We've got our R squared. So we've got a mass 1 times mass 2 equals mass squared. We've got a length times length 1 times length 2. We've got an R squared. We throw in our proportion of gravitation, our Newtonian gravitational constant. We're going to get approximately that negative 10 to the negative 26 Newton meters, or a small unit of force. Okay. We divide it by the bending stiffness of our realm, Hbar c. We take the square root of that. We're going to get our inverse meter. We multiply that by 2 pi. And we divide that whole jazz into Planck momentum. And at least, according to just the units on Wolfram Alpha, it seems to be 1 joule second to about 3 decimal places. Now, okay, it is not 1. We do not have unity. And then again, we're going to have to follow experiment, but you realize we only really know the Higgs to about 3 decimal places. This seems to cover the gap. And what I learned from that is you look at something, you're like, maybe this is telling us something. What would we need to do for it to be true? And that's basically where we came to this whole, well, what if it was supposed to be 1? What if it was proportionally the root of action, so to speak, between that? Because you could just rewrite this whole dang thing as... because algebra is awesome. Take the unit of joule seconds. Divide it in. 2 Hbar, you just move it to the other side. So we're dividing it out there. We divide it over there. It's telling us to true. Hold on, let me throw the little pretty things around Hbar just so it looks prettier. There we go. All right, so this is the claimed relationship. So you got your unit of action divided by the reference of action. Again, this is kilograms, meters squared. This is literally this. Hold on. It's kilograms times meters squared divided by seconds. Actually, no, because we're multiplying by second. It's kilograms times meters squared divided by 1 second. Why the heck should this have a relationship here? I mean, okay. Assuming that this relationship's whole, let's entertain this idea. Why the heck might this be the case? Because at that point, now we're making the claim that not only is the kilogram, the meter, and the second are meaningful. Now, I can just sit up here and just kind of hand wave and be like, well, they're based on constants of nature now. It's like Hbar is based upon, the kilogram is based upon Hbar, which is now defined at 10 significant digits. So basically, we can use that and basically the Kibble press and everything. So if we can tell something's mass, it should have an associated energy and then be a charge. And those relationships, basically these relationships that we're kind of going through here, we should be able to determine its mass. And again, I realize I'm redoing, going to post the update this week because I do actually need to present my actual project in another locale, and I need to add a section. But basically, that's kind of what we're going over. We're looking at these relationships. What is it? There's that. The speed of light, length is now literally based upon the speed of light. Okay, so we're getting that out there. And then the second is the hyperfine transition of cesium-133. Does it have anything to do with that? I don't know, that's the first radioactive element that's closest to 137 that we can use to do those things. There is a cesium-137. There's also another 137 element, but I think it's stable. It's not lithium. Lithium is the third element. I don't know. I mean, my closest estimation about why might this be, I'm like, well, the Planck momentum is number one, where we are kind of invoking it over. Hold on. Oh God, I've gone too far off the. Hold on, enlarge this. Thank you. There we go, much better. All right. So, number one, the Planck momentum is here. Why is it that, I don't know, momentum seems to travel through space-like hypersurfaces, and energy seems to travel through time-like hypersurfaces? Might it have something to do with something that Rick was talking about a little bit earlier? I don't know. Maybe it is. Maybe it isn't. Rick is saying that gravity is equivalent to acceleration. Well, it is an acceleration. It's an acceleration it's a volumetric acceleration of a mass, whatever that might mean. It's because you got a length. You've got your time squared in the denominator. You got two more dimensions of length to give you a volume, and then you got a mass in the denominator. Yeah. It is an acceleration. Which is kind of interesting because, well, if h bar c is basically big G with mass in the numerator, would that mean that's an acceleration as well? It's got a volumetric acceleration, but mass is in the numerator. How weird. The other thing that one might say is when you're going through the projects, you're going to find the kilogram was technically originally based upon water, because even if you just do even now today, water is such a useful thing. And then Michael Hughes has been on Demystify Psi a couple of times, but even he's like, going over like 60 years of the literature and water and everything, he's like, there seem to be some really weird things here. Like, there seems to be some form, I don't know, like causal propagation. There's like, you wouldn't think that things should be able to propagate at quite that speed. It doesn't seem right, but because of how water is shaped and everything, it's pretty good at sticking together, so to speak, and has very interesting properties. But long story short is 1,000 kilograms. Even just on Wolfram Alpha, if you look at this, it's approximately 1,000 liters. Basically, a liter is, well, it seems to be about 1 kilogram. Again, assuming the conventional density of 1,000 kilograms of water, or basically 1,000 kilograms is approximately 1 cubic meter of water. Now again, H2O, maybe just water density. So the density of water, it's about that. So it's about 1 gram per cubic centimeter. Now again, it does deviate there, but this is just our general where we are. I don't know, I guess one could imagine, I know Rick has postulated that you're just a little bit under the surface level of water, and perhaps literally a pinch of salt. Basically, there is a pressure and temperature. Well, those are associated, but pressure and temperature where water should be precisely 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. I mean, if you could postulate that, but then you run into the crazy kind of chicken and egg paradox. It's like, wait a second. How could this possibly be the case? That you're going to base water on your system of units? Water didn't exist before this. So it's like, well, if we didn't even have hydrogen, but this is a basis for a system. I mean, I don't know. Maybe we're going into, I don't know, a lab experiment that some higher dimensional being was like, I got a cubic. Are we getting into the Futurama episode of where do we live? Are we just the universe in this box? And I don't know. I mean, that's a wild speculation. Some folks may love that, but it's, I mean, at that point, your argument would literally hold water, but to justify that, I mean, you'd have to be literally mad. I mean, you'd have to literally be a mad scientist to propose something like that. But, all right, Rick, have a good dinner. Yes, it's a wild thing, and that's, they just go into history. I'm like, okay, that's interesting. Water does have effects, but again, that's a future discussion for things that might need to be shared at different times. So let's get back to at least what we have, at least what we can calculate, rather than going into the wildest of speculations. Okay. Now here's the thing. A wild speculation doesn't mean it's not true, but you're going to need to follow the evidence. So the evidence that at least I claim we're following. I went too far off the farm. Let me go back. There we go. All right, so all this jazz here. So we've got all our stuff here. So basically the proportional thing with the Higgs mass and the Higgs wavelength. You got your big G, mass 1, mass 2, divided by r squared. You divide it into the bending stiffness, h bar c. You multiply it by a circle. You divide it into the Planck momentum. And basically you get 1 joule second. Okay. So this whole thing comes in if we assume that maybe this crazy relationship was true. Basically, this sets the proportionality or dimensionless proportionality, which we can do via our other way where we... what did we do? We did... What was the formulation? The formulation was Higgs mass. All right, so we did the Higgs mass squared. We divided by 1 over big G. And then H bar. Let's see. And this is what we did to get our dimensionless number. Oh, sorry. Okay. So basically this gives us the magnitude of H bar, and we didn't shove in the Joule second there. Okay, that's just, if we were to do this and we did the square root of this, should be about 10 to the minus 17, or about the difference between the difference in scale between the Higgs mass and the Planck mass. And if we multiply this by the Planck mass, we can get something of the order. Okay, so about 125.2 GeV. Again, we're basing this off of just the Wolfram alpha numbers. We want to put in the information we have from CODATA. Let's throw that in there. Let's see if it gets a little bit more accurate. Okay. So, what is that in GeV? I remember it most. That should be about a 0 and then a 3 there. Okay, okay. So it's getting a little bit closer. And again, we've already input that number there. So again, maybe this is just numerology. Maybe it's like, I'm putting in a thing, I'm getting a similar thing. I don't know. I mean, these units are just mostly what's on CODATA and everything. So it's put in these numbers, I get that number there. All right, I get about 2 pi joule seconds. I throw it in the denominator, it divides out, we get approximately 1 joule second for at least, well, we only have 4 significant digits, so maybe it's going to wildly deviate after there, and it's not actually pi. Maybe, maybe not. But I'm coming at this from multiple perspectives rather than saying, oh, this is an interesting thing. It's like, that's interesting, but if I'm literally just throwing in a joule second there, that's not very satisfying, because I'm literally just throwing that in there and saying, oh, this is going to hold here. Maybe it does, maybe it doesn't, I don't know. And again, there's only so much information there, but we need to go where we can figure out maybe what's going on. Or basically, if we'd see these relationships, it's like, well, maybe if hypothetically this whole if this whole dang thing was true, and again, this is a hypothetical, if we assume that this 2 pi was a factor there, that's a dimensionless thing. We got that to basically as many digits as we can compute. So if we assume that this factor should be there, then these other parameters that maybe we've calculated based upon measurements and we've derived them, or maybe we've actually measured it, if we have the ability to hook onto something that does seem to be dimensionless, well, then these parameters should fall within that range. And then if you deviate, it's like, maybe there's another level of reality, or maybe we're just wrong. Most likely we're just wrong if we start to deviate, but seeing is, and again, I did all these things. I'm like, what would I have to do for this to be right? And oh God, the number of hours, and just, I don't know, eventually you divide it into something and it's like, multiply by 2 pi or something like that. I think maybe that's what I did. Hold on, how did I even figure this out? All right, so I did. Oh, okay. Here's how I figured it out. All right. So long story short, I didn't even remember. All right. So we divide that in number to get it manageable. So I'm like, I see this. It's like, well, that doesn't really make sense to me. Because I think I tried to look for a closed form, but you only have 4 significant digits there. You can only insert so much data. It's like, well, what if I multiplied it by, I don't know, a circle? Okay. The only reason I know this is just because these first couple of digits, it's like 6.524 or 5. Technically, it's probably 4 and 9 or so. This seems to be about the magnitude of, well, the Planck momentum. How do I know that? I'm just a crazy person that sometimes remembers the first couple of digits of things. 6.525. Again, different dimensions. 6.524. Okay. It's got about 3 significant digits accuracy, and when you actually do the calculations, it probably is rounding up to, it's probably 4.9. So it's rounding up there. I'm like, okay. Well, if that's the Planck momentum, what if I assumed it was true? Okay. So originally, I think I divided the Planck momentum in it, and it gave me something inverse angular momentum. So I'm like, let's just divide this into the Planck momentum to get nicer units. And then we get the reference of action out. Note, in here, this whole thingy, it's based upon big G and the claim that, okay, to be fair, okay, I am inserting the Joule second here, although we don't need to insert the Joule second for that to do that. All we need is, sorry, too many comparisons. Where's my, oh, far too many tabs. I should probably just have a bunch of notebooks. Hold on, okay. Basically, you could also derive it from this. So you're taking literally the mass of the Higgs. This is just the dimensionless coupling thing that they showed, that basically if you change this to elementary charge, if this was the electric constant rather than the inverse Newtonian gravitational constant, you're going to get, let's just do it, elementary charge divided by that thingy. So we've got the square root there. This should give us the amplitude of the fine structure oh, God. What did I do? Oh. Because I didn't put in the electric constant. There we go. All right. Oh, excuse me. It's supposed to be 4 pi. We got our 4 pi. 4 pi epsilon. There we go. And then if we don't take the square root of that, we get the fine structure constant. Because now it's got charge squared. And this whole dang thing at the bottom is also charge squared. Units cancel out. Dimensionless number. Fantastic. I realize I'm probably just repeating myself here now, but long story short is we're just taking this, we're noticing this relationship. Well, it seems to be a way to get out some dimensionless things. What if we assumed it was true? So, and then that leads us in conjecture here. We take that mass number, we go through, we calculate our wavelength. Mass 1 of Higgs 1, Higgs 2. Mass 1, mass 2 squared, R squared, gravitational constant. Really small force. Again, same thing happens when Coulomb's constant when we divide by voltage, or at least the mass energy of the Higgs. We do the same thing, we get the same force. Again, that shouldn't be surprising. We divide by bending stiffness, or, oh, actually, this, I may not have read this one before. Inverse distance potential coupling constant. I mean, that does sound like what it's talking about. It's literally an inverse distance, and it's via coupling constant. Contact density, or image potential energy gradient, whatever that may be. Well, liminal, I'm going to make the claim that numerology is numerology until it explains more with less. And Legend has it, and again, this was from, I think, like a history of the universe video or whatnot, so take it as you would, but I think it was one of those folks that does a long form analysis about like the history. They'll actually show the math and everything like that, and they'll actually go through, and it seems to be pretty good, and I'm pretty sure from actual teacher, so it's actual physics professor, so it's pretty good. But long story short, as what was I talking about? The legend is that Max Planck, when you had the ultraviolet catastrophe, why? What was that? Our original classification, I think, when we were using Wien's law or something like that, there was one form where basically as your wavelength got smaller and smaller, it seemed to trend towards infinity. And it's like, well, this doesn't seem to be what's actually happening. What do we need to do? So basically, I don't want to say it's necessarily a kludge, but it was said, at least in a video, that Planck, in a moment of desperation, was just like, what do I need to insert to make the data fit? It was about, I think, 92.3 nanometers or something like that. I don't know. Is this why we have electron volt nanometers? Because there was something about like a particular wavelength that you put in, they went through, and ultimately you get your reduced Planck's constant, your 1.05 times 10 to the minus 34 Joule seconds that also happen to have the units of action. So, well, maybe if, I don't know, is he just using the principle of the minimum of action to find the minimum of action to work within our realm? Again, I ain't no Max Planck. He had to look at the data, and again, I'm pretty sure he did this when he was a lot younger. We have so many more measurements. We have computational tools and stuff like that. So I just meatbag like me can go blah, blah, blah. What is this? What is this? You do it enough. Again, is there something significant here? I don't know. But I just put that in. I'm just like, all right, big number. I don't understand. Let's get it to a smaller number. I don't understand those units. Let's just take the square root of it. Okay, that's got a little smaller. Still don't know what it is. What do I have to do to figure out what it is? The long story short is I multiply by 2 pi. It looked to be the inverse of this. So I'm like, oh, let's just divide this into this so we get nicer units. Well, this looks like 2 pi. Because when we put in 2 pi, we get down to 1 Joule second. And again, this is dimension hopping. This is numerology, but okay. Maybe I should just expect this. I should just expect this because ultimately, at one point or another, for this one, we are inserting the Joule second, or we are literally dividing the elementary unit action. Or at least we assume that because we can just do this as well. It's a little bit off, but oh, what you could also do is where was it? The other one. You could also just take the most recent measurement too, plug it all in. So, because the most recent measurement is, it's within 4 mega electron volts, or 0.004 giga electron volts. It's within this technical prediction. Again, doesn't mean there's anything there, but I just think it's kind of cool. Oh, and there are other ways you can do this, where if you take that force, you multiply it by the Planck force. This is probably the easier way to just do it. You take that number, you divide into the Planck force. You get a ginormous number, you take the root of that number, you multiply it by Hbar divided by 2 pi, and then you also get a 1 Joule second. So again, I'm just looking for the combinatorial relationships here because, okay, if we can go this way, we can go that way, and these can line up at unit 1, it does becker the question because at least it it's not saying approximate, so at least it seems to at least hold to 4 decimal places. We've got pi to, I don't know, millions, billions, quadrillions of decimal places and stuff, so it's at least a method of attempting, as we probe deeper into reality with higher and higher precision, trying to figure out what the heck's going on. And if there is something like 2 pi, 4 pi, it's the difference between, well, Planck's constant and the reduced Planck's constant is literally 2 pi, because Hbar 2 pi gives us Planck's constant, because they define Hbar as Planck's constant divided by 2 pi. And so basically we're kind of taking the cycle out, so to speak, or at least that's how I kind of think of it, because, well, it's literally a circle. So a lot of this is just kind of also an exercise for me to try to, like, okay, am I just doing the same thing in a different way? Or is it all combinatorially equivalent? I say combinatorially equivalent because, well, if it's combinatorially equivalent, we should be able to take some information to a particular limit, put it on a computer, and then there should be a computational equivalence within our limit. Because, well, if you want to know exactly what's going on, you might need to literally simulate universe or have a computer the size of a universe. So, all right. Oh, God, I've been rambling for over an hour. I need to go get some dinner. So, all right, that's all I got for right now. Again, there's links in the doobly-doo. And again, take this as it would. Does it actually mean anything? I don't know. It's just, if you have something, it's like, it seems to be interesting. This seems to match data pretty well. Just doing what I learned from Thad. What if I assumed it was true? Because if I assumed it was true, maybe we can learn something. Maybe it's just another dead end, but it seems to be interesting, and I do kind of get addictive because it's, oh, what is this? What is this? And then a lot of the time, it's, as you can see from my tabs that I had there, I get very scatterbrained, and then I have this. We'll go into some other stuff a little bit later on another day, and let's just say I see things and I remember what people tell me. And then it's like, well, sure, is this even worth looking up? And then you double check. And I'm not saying that we may have potentially found a way to calculate the limit of the fine structure constant within QED. But I found a very interesting number that's interesting. We'll talk about that another time, but with that said, take care of yourselves, everyone. It's a wacky and wild world out there, but it's open for a better tomorrow.